Let's proceed with the natural response of a series RLC circuit. So applying KVL at loop I, so we have VR plus voltage across the resistor plus the voltage across inductor plus voltage across the capacitor equal to 0. Now take note that the voltage across the inductor can be expressed as LDI dt, or the current in a capacitor can be expressed as C dV C dt, or in terms of, or the voltage VC can be expressed in terms of I, this equation, 1 over C integral of I dt plus the initial value of V. So now in terms of I, VR is just equivalent to I times R, so following the passive sign convention, plus LDI over dt plus 1 over C integral of I dt plus dO equals to 0. Now differentiating this equation, so becomes R times di over dt plus L times second derivative of I with respect to time plus 1 over C I equal to 0. Now rearranging this equation, second derivative of I with respect to time plus R over L di over dt plus 1 over LC I equal to 0. In terms of voltage VC, our equation becomes, I can be expressed as this equation, C dV C dt. So VR can be expressed as R times C dVC or dt plus I. So take note that I is C dV C dt. So we have LC, second derivative of VC with respect to time plus VC equal to 0. Now rearranging this equation becomes dVC dt plus R over L dVC or dt plus 1 over LC dC equal to 0. Now take note, you look at this coefficient, these coefficients, so they are just the same. So we can say that the expression for I and V are of the same form. Now solving for the roots, solving for the characteristic roots, we have S1 and S2. So this is equivalent to negative R over 2L plus minus square root of R over 2L squared minus 1 over LC. Or this is just same as negative alpha plus minus square root of alpha squared minus omega naught squared, where the value of alpha just R over 2L and our omega naught 1 over square root of LC. So the same cases applies to the series RLC circuit. So we have overdamped, critically damped, and underdamped. Alpha greater than omega naught. So the expression, for example, IT is equal to A1 e to the S1t plus A2 e to the S2t. So this is for overdamped circuit. So for critically damped circuit, or where alpha is just equal to omega, our expression for I of t, we have A1t e to the negative alpha t plus A2 e to the negative alpha t. Now for the last case, so the underdamped case, where alpha is less than omega naught, expression for IT, for example, e to the negative alpha t times the quantity P1 cosine W dt plus V2 sine WD t, where WD just equal to square root of omega naught squared minus alpha squared. So let's have our first example. So if L is equal to 1 Henry, R is equal to 2 kilo ohms, and C is equal to 1 over 401 microfarad, and we are given the initial values of I and VC, find the expression of I of t. First, let's determine the values for alpha and omega naught. Alpha is equal to R over 2L equal to 1000. Our omega is 1 over square root of LC, which is approximately equal to 20,025 rad per second. So we have, for alpha is less than omega naught. So we have an underdamped circuit. So we need to solve for omega d is equal to square root of omega naught squared minus alpha squared is equal to 20,000 rad per second. So for an underdamped circuit, for I of t is equal to e to the negative alpha, so we have negative 1000t, 10,000t times the quantity V1 cosine of 20,000t plus V2 sine of 20,000t. So this is expression for t greater than 0. Now at t equals to 0 plus, we have initial value of I, which is 2 milli, so we have 2 milli equal to B1 plus 0. Our B1 is equivalent to 2 times 10 to the power of negative 3. Now to get the value of B2, need to integrate this expression. So di dt of this expression is just negative 1000 e to the negative 1000 t times B1 cosine 20,000 t plus B2 sine 20,000 t, and plus e to the negative 1000 t times negative 20,000 V1 sine of 20,000 t plus 20,000 B2 cosine of 20,000 t. So at t equals to 0 plus, we have di of dt at 0 plus is equal to, so we have negative 1000 times, so b1 is just equivalent to 2 times 10 to the power of negative 3 and plus 0 plus 0 plus, this is 0 plus 20,000 b2. So what is di over dt at 0 plus? Di of dt of 0 plus. So take note that our VL can be expressed as L di dt. So our di dt is equivalent to VL over L. So at time was 0 plus, di of dt 0 plus is equivalent to VL of 0 plus over L. What is our VL of 0 plus? By applying KVL at this loop, we have VR, voltage across resistor, minus VC plus VL is equal to 0. Our VL is equal to VC minus VR. So VL at 0 plus is equal to VC at 0 plus. Then our VR can be expressed as I of 0 plus times the resistor R. So we have VL of 0 plus just equal to negative 2 volts. So our di dt of 0 plus is equivalent to VL of 0 plus over 1. So this is equivalent to negative 2 amperes per second. So this equation just equal to negative 2. Now solving for the value of B2 is just equivalent to 0. So our expression for IT just equal to 2e to the negative 1000t cosine of 20,000 t u of t milliamperes. Now this figure shows the graph of I of t. The graph shows a sinusoidal wave with decaying amplitude because of this factor e to the negative 1000t.